All right, so today I will be talking about, just one more thing about current, and then we will start talking about what are the sources of current, how actually we drive current in the circuits. I think that probably you know a lot of this stuff from kind of common knowledge, which you are going to see on this slide. It is a distinction between something which is referred to DC and something which is referred to AC. DC refers to alternating current, and DC to direct current. So if the charged particles move only in one direction, then we refer to this type of a current as direct current. DC stands actually for the current, the phenomenon. DC means that the charged particles flow in one direction. Well, it happens that the physical quantity is either positive or negative in this case. For direct current, if we consider current, the quantity across one of the cross-sectional surfaces of the conductor, then it will have one sign. Now, an example of direct current, and actually I want to start with an example which is maybe not the most typical, but for example the battery charger or an alternator in the car delivers direct current to the battery. However, that current is usually not constant. It oscillates. A battery itself, when you connect something, then if you consider a relatively short period of time, like a time when you start the car, or in a flashlight, for example, it could be even hours, but not a year. On a year scale, no matter what, that current in the flashlight is not going to be have this property. And what I mean is that the current value is independent of time. When you talk about DC, or direct current, then first should come to you that it's not only flowing in one direction but also constant. Although direct current doesn't have to be constant. Now, however, where there was a big fight, kind of mental fight, sometimes in the past between Edison and Tesla, how to distribute electricity among population. Tesla wanted to do it using alternating current, and Edison wanted direct current, like the one we just described. Alternating current, which Tesla introduced all our households now receive this type of a current, means that the charged particles move in both directions, and we refer to this, an acronym for it is AC. Now there are various reasons actually why Tesla's argument won. One is that it is easier to produce, and the other one, it is easier to transform. So it's easier to save on the transmission lines, because what we do is in a power station we convert whatever generator produces into current, maintaining high potential difference between the wires which transfer energy from the power station to a city, and then in a city we transform it back to the current which we have our outlets. so the potential difference is lowered back to, lowered to 110 volts. But between the cities, potential differences in thousands of volts. All right, now we get electricity from devices which are referred to as sources of electromotive force. And it is any device that by doing some kind of work, it is capable to maintain a potential difference between terminals of that source. If we get something like this, we have a source of electromotive force. This is the symbol for a direct current source, and actually we have these sides refer on which side we have higher potential and on which side we have lower potential. So the longer line means that this device is transferring charge in such a way to maintain higher potential on the left-hand side. Yeah, the longer line corresponds to higher potential, shorter line corresponds to the lower potential. The source of alternating current source, this is the symbol for such a source, and actually the symbol inside that circle will resemble how the potential difference varies. So for example, the one which we have in our households, it's a sinusoidal, so here I made a drawing of a sine function. But we can have a square function, triangular function, and whatever is shape of the variable alternating current value will be indicated in this circle. Now here are some, where we really get energy to produce electricity. There are a lot of sources of electricity. The most common and the one which is used on the largest scale is electric generator. And in electric generator, we crank the generator, it turns around, and actually we can turn it in many ways. So although in the generator we convert mechanical energy because it is rotating, rotor in the generator is rotating and it produces electricity, there is always something which has to run the rotor. So for example, in a power plant, coal or oil is being burned to run turbine using the steam generated from that coal, and then that turbine turns the generator, which eventually converts it into mechanical energy. There are hydro plants, for example, in which rather than steam turbine, we have a turbine which is run by the falling water. In a battery, and it doesn't matter of the size of the battery, it could be one of those tiny batteries which you place in electronic watches, it could be a battery in a flashlight, or it could be a battery which you have in a car. It uses chemical energy. There is a chemical reaction, and through this chemical reaction, charge is being transferred from one side to the other side. Well, solar energy becomes quite popular recently when we are facing crisis of energy. So now people are putting solar cells on their roofs and produce electricity that way. It uses electromagnetic radiation coming from the sun and converts it to electricity. And actually solar cells, well, they are used in calculators or in commonly or electric fences, sometimes somewhere in fields, or to illuminate paths in the gardens. Actually, it combines a solar cell together with a battery. So during the day, a solar cell produces electricity, charging the battery, and then when darkness comes, the battery takes over and it's getting discharged, and the next day the solar cell is recharging that battery. However, with the solar cells, we are also now creating electricity by putting panels on the roofs of the houses, and then that energy this electricity is connected to the household wiring, and on a very sunny day you can even have a surplus of energy generated, and you will put it back to the grid. Doing this actually has a certain serious problem, which we are, as a humanity, we are still working on it, how to adapt solar cell to the electricity grid, because a problem is that solar cell produces a direct current, and from the time of Tesla we have alternating current, so we have to transform somehow this direct current produced by solar cell into sinusoidal current produced by the solar cell. Thermopile uses internal energy of a system, so really the way it works, it has two identical contacts kept at two different temperatures, and if something like this happens, the thermopile will produce potential difference. Thermopiles are more used for measuring temperatures than for producing electricity. So it is still not a source of electricity, although it produces electricity. The same way, by the way, like living cells. Living cells also produce potential difference, and actually our nerve systems work because neurons have different potential inside and outside, and when we want to send a signal from brain to the muscle, or the other way, it is, when we say that neurons fire, and when they fire, really it is that they affect potential difference. There is a tiny well, actually, it's not that tiny. It's pretty measurable. It's of the order of 90 millivolts. Potential difference between the inside and the outside of the cell neuron is about 90 millivolts. And whenever signal is transmitted, it drops actually to zero, and then is being discharged. And how fast it is being recharge and discharge relates to the intensity of the stimulus which is received by the body and transmitted to the brain. All right. Now, the sources of electromotive force, which you can actually also think that these are devices which produce potential difference, they are characterized by a physical quantity called electromotive force. So electromotive force is a quantity which tells us how this particular device is going to work. Now, by the definition, electromotive force is the amount of work per unit charge performed by the source in attempt to maintain the potential difference between its terminals. Yeah, because it is that if we have, how about if we see it? what happens is that when we have a source, there is some kind of mechanism. In a battery, for example, it's a chemical reaction. In a solar cell, it's operation of the p-n junction and separation of a charge on a p-n junction. No matter what the source does, it is moving charge from one of its sides to the other of its sides, or from one terminal to the other terminal. And, well, it continues to charge. I mean, think like over here. dq is, in order to produce potential difference like this, that here we have higher potential, here we have lower potential, the device is supposed to move positive charge from the bottom to the top. And it is doing it. The source of electromotive force, each source of electromotive force moves positive charge from the negative terminal to the positive terminal to maintain, to create this potential difference. Now, do you recall that our discussion on how much work is done on charged particles when we move from one plate of a capacitor to another plate of the capacitor? Which electron is it easier to move, the first or the second? The first. And fifth or sixth? Fifth, right. Yeah, because as soon as we move transfer charge, the electric field is created in the other direction, right? Think about it. If we transfer positive charge from this side to this side, we will have higher potential here, lower potential here, so electric field in the battery is going to be downward. Now that chemical reaction is supposed to move charge against that field. The force exerted by earlier transferred charges, earlier transferred particles, pushes it the other way than the reaction. So this reaction actually will continue until the electric field produced in that source is sufficiently strong to prevent further reaction. The reaction would stop because for the reaction to take place, it would have to transfer charge from one side to the other side. And eventually, it will require so much work to transfer that the reaction will stop. However, if I connect now this terminal with let's say, a light bulb, I will be taking away charge from the terminals. Well, if I take it just by a tiny amount, the reaction will push another electron. Do you understand that? Can you imagine it, how it works? Yeah, so if the loop is not closed, so that charge transferred from one side to another side, which creates that electric field, suppresses the reaction, and the battery will do nothing. If we now close the circuit and we remove this transferred charge, the reaction will replenish it, all the time transferring charge from one side to another side. All right, and electromotive force over here, we have work which is required to transfer a charge from one side to the other side per unit of this charge. You will have a quotient. Yeah, this is amount of work done by reaction, for example. Yeah, the chemical reaction results in this work. This is not work done by the electric field. Or it could be by a p-n junction taking energy. So electricity is not the source of this work. It's that whatever mechanism the source uses. And here is that if we divide now this amount of energy by the amount of charge, we will get how much work is performed on a unit charge. Yep, work per unit charge. Well, now let's think about an ideal battery in which the the only thing against which this agent has to work is the electric field produced by the by charge difference and potential difference between one terminal and another terminal. Yeah, so if there are only those two interactions, yeah, the interaction which pushes charged particles and the electric field produced by the transferred particles, then this work is going to be opposite to the work performed by the electric field. Now know that work done by the electric field is negative. Yeah, because electric field is down, right? Charge is moved up. Positive charge is being moved up. So right. So force is downward. Displacement is upward. Yeah, electric force. So electrical work is negative. This one is positive, right? Because something is pushing it upward and the particle is being moved upward. Now, but if there are only these two interactions, therefore these two works will be opposite. Now, I can write down explicitly this work, this electrical work, using, for example, concept of potential energy and potential. Yeah, electrical work is opposite to the change in potential energy. So I wrote change in potential energy. I put that minus, and now this is potential energy of the charge when it is over there, and this product represents potential energy of this charge when it was here. So what I got over here is the change in potential energy of this charge Q when it was moved from the bottom to the top. Well, and it is the electrical work. Well, this minus with this minus cancels, and dq cancels, and I'm getting that this V plus minus V minus. So actually, if there is only, if the work is used only to increase potential difference between the terminals of the, or to maintain potential difference between the terminals of a battery, then electromotive force is equal to potential difference between the terminals of that source. It's not the case in a real source, because when current flows, some of that energy is also used to maintain that current. It is that the lattice is going to perform additionally negative work on the charged particles, and we will see how it is incorporated into the relationship between potential difference and electromotive force. However, if current does not flow in a source, then you can, and probably for technical purposes, it is the best to remember that potential difference between the terminals of a battery when the current doesn't flow is equal to electromotive force. Now, if we think about let's say AA battery, or D battery or C battery, when you go to buy it, it says certain amount of volts. Anybody remembers how many? 1.5 volts, correct. Now, and probably you believe that this is potential difference produced by a battery. Who believes that? Let's see. Who thinks that 1.5 volts is something else, that it is current flowing in the battery? Who believes that it is current flowing in the battery? That's good that nobody believes it, because it isn't current. It's better to say that it is potential difference between the battery, but this is potential difference only under certain circumstances. Because now think, what will happen if I have this battery and connect the two terminals with the wire, with a piece of wire? Now, wire is an ideal, let's say that I have this ideal resistor whose resistance is 0. Well, current will start to flow with that wire in, and if I take AA battery, it will be of the order of 5 amperes in that wire. What will be the potential difference across the wire? 0. Right. Potential difference across this wire is going to be 0. Now note that it's the same potential difference as the potential difference across the battery. So where that 1.5 volt is. Because now you can see that there is a contradiction. Because on one side you can think about that it is 1.5 volts, and on the other side you can recognize that it is 0. Now a charged battery in a car has potential difference of the order of 14 volts. A discharged battery will have about 11 volts. Now what will happen if I connect charged battery with a discharged battery? What potential difference are we going to have? 11 or 14? Well, we'll talk about this a moment later. If the current doesn't flow, then the potential difference is equal to electromotive force. This 1.5 volts on an AA battery is the electromotive force of the battery. It is not the potential difference between the terminals of the battery or voltage across the battery. It is indeed voltage across the battery when the battery is not used. When the battery is used, that potential difference is different. Yeah. Now, I already mentioned that a charged battery in the car has 14 volts. It has 14 volts when it is disconnected. If you take a voltmeter and measure potential difference across the terminals of the properly charged battery, it will be about 14 volts. Now, what voltage a battery in the car supplies here in America? 12. Yeah, the rating of that battery is 12. But this 12 is required that when the battery is used, that it maintains that potential difference. You can, when you turn on your stereo headlights, probably not when you turn on the starter. When you turn on the starter, the potential difference drops lower. But this 12 volts is supposed to exist when the car is on and the battery is used. I mean, when the ignition switch is on, not that current is, not that the car is running, because when the car is running, actually the battery is disconnected from. It is being charged by the alternator. All right, now this potential difference, from the relationship between potential and electric field vector, we can also recognize that electromotive force is just a line integral of electric field between this point and this point. All right. Let's now take a look at real sources of electromotive force, like a battery, for example. Voltage produced by a real source of electromotive force is related to the electromotive force itself. However, it is less. Potential difference between the terminals is equal to electromotive force minus product of a current and a certain parameters characterizing the battery or the source of electromotive force, and this parameter is called internal resistance of the source. So practically a real source or a real battery always behaves like a source, ideal source, connected in series with a resistor. Now I don't want you to think that really we have a battery and a resistor in a battery. when we make the entire system just behaves like such a combination. So, for example, if we have a 1.5 volt battery, it means that the electromotive force is 1.5 volts, and we can think that we have the potential difference between this point and this point in the battery is 1.5 volts, but then we have also a resistor. So if we close a loop now and current starts to flow, what happens? Compare potential at this point with potential at that point when current flows this way. Let's say that this is the conventional current. If this is conventional current, potential here or here is higher. Who believes that potential here is higher than potential here when conventional current flows that way? Potential here is higher than potential there. All right, who believes the other way, that potential here is higher than potential there? And your brainstorming was a little bit suppressed. I think that it's by the fact that it's Monday today. Well, I saw at least one vote that potential here is higher than potential there. And it is true. When current flows in the battery in this direction, then potential difference over there is higher. And Andrew, can you justify your statement?
I was just recalling the diagram with just the VA, VB, and just you take just if you think of the battery.
Which diagram are you talking about?
Two slides or
back.
Of a resistor.
Of a resistor, correct. You should have recall the slide with the resistor. If current flows this way, positive current gives a positive value for a product of current and resistance. Now that positive product is supposed to be equal to the potential difference between this point and this point. Tail of the arrow and head of the arrow. Yes, so this potential minus this potential gives me a positive number, which means that potential on this side has to be higher than potential on the other side. How about, why don't we now think about some examples before. Let's go through the measurements. And we will start tomorrow's class with the examples. Now, in order to measure electrical quantities, we need meters. So, for example, in order to measure current, we use a device which is called an ammeter. Now, let's say that I want to measure current flowing in this resistor. Well, if I want to measure current flowing in this resistor, I have to connect a device in such a way that I'm sure that the current in the ammeter is going to be, well, at least the same as in the resistor. Therefore, we have to insert ammeter in series with the device in which we measure current. So, like in that arrangement, current in the resistor is going to be equal to the current in the ammeter. Now let me ask you a puzzle. I'm going to give you a puzzle. How about current in the light bulb? The current which I will measure on this ammeter is the same as the current flowing through the light bulb or not? Who votes that that yes, current in the ammeter is going to be the same as the current in the light bulb? So in this arrangement which you see on the drawing, this ammeter simultaneously measures current in the resistor and in the light bulb. Who believes that it's true? 1, 2, 3, 4. Who believes 5? That it isn't 1. So, William, you believe that the current in the light bulb is what? Smaller or higher than the current indicated on the ammeter? Smaller. And what's the reason? Because the length of wire will act as a resistor, and therefore what? Current will drop, right? So where those particles would go? Because when current drops, it means that fewer particles is being transferred through a surface. So what will happen with those particles? Well, actually, William doesn't give a correct justification. William confused what with what? Current and voltage, correct, or even more accurately, potential. Because indeed, potential at this point, or let's say at this point, is going to be different than potential at this point, because wire is a resistor. So potential along the wire changes and it drops. Potential here gets smaller and smaller. Now if this wire is good, it will be, let's say, 1,000th of a volt, but indeed it will drop. Now, whether elements are connected in parallel or in series, we have to think what will happen with the charge. Well, if certain amount of charge enters this resistor, the same amount has to exit the resistor. The same amount will enter ammeter, and the same amount would exit ammeter. And therefore, the same amount will enter the light bulb and exit the light bulb. The charge doesn't get compressed anywhere. There is only one device which has this capability, accumulating charge at a particular place. What is it? Capacitor. Charge on the capacitors can change, but in the wires, no. How about current in the battery? Can I figure out the current in the battery, or do I have to put that place the ammeter at a different location? Who believes that the current measured on that ammeter is equal to the current in the battery? Let's vote. Who believes that yes, it does? 1, 2, 3, 4, 5, 6. You are right, because whatever charge enters this and exits that way, it has to enter this way and exit that way. You have to think about that current. You should see the charged particles traveling, and they don't get accumulated in any place. It is like a tightly packed crowd going, let's say, through the corridors of this building. Now, unless somebody moves a little bit further, you have no room to get there. Well, so however, if this entire thing starts to move, then we will have indeed current. All right. Now, when we use an ammeter, we don't want really that ammeter to be a part of the circuit. We want to introduce it only temporarily, and then remove it and connect it with the wire. So normally the circuit, in that circuit, this wire is supposed to be connected right to that resistor. Therefore, ammeter should behave like a piece of wire. And in order to behave like a piece of wire, the resistance of the ammeter must be small. All right. Now, when we want to measure a potential difference across an element, we have to make sure that the potentials between the terminals of voltmeter are the same as the potentials across the element. So let's say that I want to measure potential difference between these 2 points. then I have to connect a voltmeter parallel to this to the device, like that. By the way, I marked actually the terminals of meters with red and yellow colors, because when you connect a meter, it says which side is supposed to be connected to higher potential and which side is supposed to be connected to lower potential. If it is an electronic meter, then it doesn't matter, because the digital display will say either plus 1.5 volts or minus 1.5 volts. However, if there is a galvanometer, and particularly if 0 is on the left-hand side, so if you properly connect, the arrow will move along the scale. If you improperly connect it, then the arrow will tend to turn the other way. You will not be able to read. All right, now, how about if I want, can now this voltmeter, does this voltmeter tell me what is the potential difference across the battery? Who votes that yes? Who votes no? Okay, William, this time you are right, and what is your argument? Right. Will recognize that this voltmeter is not connected in parallel to the battery. Yeah, we have that this potential on the battery agrees with this potential on the voltmeter. However, this potential at the battery is not equal to this potential at the voltmeter. So these two elements are not connected in parallel, and therefore this voltmeter does not measure potential difference across the battery. It does not measure potential difference across the light bulb either. I can recognize that this potential at the voltmeter is equal to potential over here by the light bulb. Yeah, because if ammeter has a 0 potential, you can think about it like a piece of wire. So potential here and potential here are equal. However, this potential here is not equal to potential there. So these two are not connected in parallel. So in order to measure now potential difference across the battery, we would have to connect a separate voltmeter. We could use this voltmeter as well and move it into that location. Now, when we insert a voltmeter, we don't want actually to alter the circuit significantly either, which means that to those charged particles traveling in the circuit, this path is supposed to appear like non-existent. We don't want significant current to flow through the voltmeter. We want as small current as possible to flow through a voltmeter. So then, indeed, no matter if we have the voltmeter or if we don't, the rest of the circuit behaves the same way. Because what will happen if I put an ammeter, if I connect ammeter parallel to the resistor? Well, then the current flowing in the circuit will be divided between the current flowing through the resistor and current flowing through the ammeter. Now, assuming that resistance of an ammeter is 0, what will be potential difference between this point and this point? 0. So placing ammeter parallel to the resistor will create potential difference of 0 volts across the resistor. What current will flow in the resistor in this case? 0, right? Because in a resistor, potential and voltage are proportional. So if I connect these 2 points in a technical slang, we will say that we shortcut that resistor, and current will stop flowing through the resistor. All the current will flow through the ammeter. So because of that, we want to have resistance of a voltmeter as high as possible. Ideal voltmeter will have resistance of infinity. Then the current flowing through the voltmeter will be zero. Don't move yet. Now, how about measuring resistance? If I want to measure resistance of this resistor, what would I have to do? Well, we use actually kind of voltmeters calibrated differently to measure resistance of the resistor. We connect that meter has its own battery and runs current through the resistors, and then it is calibrated properly. We cannot measure resistance of a resistor when it is in a circuit. We have to take the resistor out and then connect an ohm meter. And resistance and the ohm meter will indicate resistance of the element. And resistance only of passive elements can be measured with an ohm meter. We cannot, for example, use an ohm meter to measure internal resistance of a battery or internal resistance of a, well, transformer which delivers power over here. You will ruin, if you do that, you will ruin the ohm meter in a split of a second. It will be pretty spectacular, so try to do it. So, thank you very much. This will be all for today.